we derived now an alternate way to solve small oscillations. We had two ways. One was first parameterize, and then linearize. And the second was the vice versa. Now, let us assess both ways. What is the advantage of this second way? You have your parameterizations automatically. You don't need to ask for it. That's a big advantage. And the second is you reduce it to a standard model of linear oscillations. And what are the disadvantages? Disadvantage is, one of them is you may lose sparsity. May lose sparsity. What do I mean by that? Now look at these equations, for example, for the catenary. Those matrices had some form, very, very thin. But once you do such things like that, you lose everything. The QR, well, usually would, because you cannot. Yes. So that's one point. The second point is you may lose accuracy. That's not a serious thing, but it may be. I'm not able to go into more detail. If you work with standard systems which are of not very high dimension, then it is probably not so serious. But it may be serious if you are working with systems which look at your frequencies. Because frequencies are your output data for oscillations. That's the main data you are interested in, are the frequencies. Because of what? Because of possible resonances. So if you have simultaneously very small and also very large frequencies, then this computation may make a mess about them. Relatively, you work with precision 10 to minus 16. That's a typical precision in the computer. But it may happen that your small frequencies are more than that, smaller than the larger one. And you doing that, you will mess that up. So a relative small error in a large eigenvalue may be a large error. That's what I mean by that. No? And of course, the sparsity has to be compared with the general loss of dimension. This has dimension m plus s, and the other one has dimension m minus s. This also plays a role. So you have to make your choice accurately. There is one more point about sparsity. If you are concerned about sparsity, then you may say, well, I still can linearize, but I can stick at this problem originally. Here, the matrix A is the original Lagrangian. So it will keep your sparsity. So you may work with this problem to turn it into an eigenvalue problem. How? Well, just as you do with this. You say, well, x equals to x0 times e to the ei mu t and s lambda. And then you get, out of this, you get an eigenvalue problem. Oh, this m mu square minus m mu square plus ax plus pt lambda but now this is a singular eigenvalue problem. Why? It's a singular matrix. You cannot convert it to a standard eigenvalue problem. It has. But it can be treated. We now know which solutions we have, because we can at least theoretically do the elimination. So we know what to expect. But in order to solve it, you must take special methods for such matrices. They exist, and you may be able to use both advantages, sparsity and linearization. Well, sparsity is anyhow lost if you look for, if you parameterize in general. So these are just some scattered thoughts about what can expect you. So now let me do this on a particular simple example, which is very simple. The model is known to you, and I think it is illustrative and instructive. And the simple example is the simple pendulum, plain pendulum we have treated it already. Now we forget everything. We did it all. We did already and start our formalism. So what do we have? We have the Lagrangian, which is the condition, the constraint is that's what it is. Potential energy, so that's no problem. That's the input. Now, we have to compute now the dg. What's that? That's 2x to y. Motion, it's m double plus 2 lambda x equals to 0 and m double dot plus mg plus 2 lambda y equals to 0. We have here formally we have m plus lambda that's this form we have here. What do we have at the equilibrium? We have this equal to 0. So we have lambda x equals 0 and mg plus 2 lambda y equals to 0. So lambda must be different from 0, which then implies that x must be 0. That's true. Here, these are the equilibria. So x is equal to 0. And then so x 0. And what about y? Y equal to y0 equals to plus minus L, of course, because of this. And then lambda 0 is equal to mg over well, lambda is equal to minus plus mg over L. Minus means plus L, and plus means minus L. So plus L is this position, minus L is this position. First, take y0 is equal to minus L. So then we have m d over dt square xy plus, so now lambda is now positive. That means now we have to compute the second one. The condition between x and y. d2 g on the point 0 minus L has to be 0. That means x is 0. Well, that's, oh, no, y is 0. Well, it doesn't oscillate this way, but just this way in both cases. So this is a tangent space, up there and down there. And for y, you get the equation y0 for x double z plus omega square x equals to 0, where omega is equal to g over L. The standard formula for pendulum we had already. Now, that's here. Here you can also linearize, but you will then have equation mx double dot minus omega squared. And that is an exponential blow up. The solution is the exponential function, which means no stability. So now compare this equation with the one we already have obtained by using the parameter phi. How we solved our problem previously. Well, what we got? We got, I remind you, these equations are close, but not identical. How so? Well, the linearization is not unique. It is unique modular linearization. This one is linearization of this one. The linearization of a single problem build a class of equivalence. And their difference is practically nil. So it is quite interesting to look at this simple example. Okay. Now, your next exercise will be, I'll write it down, I will not solve it, and it's a double pendulum. Here you have a length L1 and its length L2. You have a gravity here, and you can do your problem in two ways. One of them is the same as I described here. The problem is find small oscillations of this system around this position down there. And the other one is to take parameters, phi1 and phi2, directly. And then linearize as I did for simple pendulum. And compare them. You must be able to get the frequencies of a system, of a linear system, which we have treated already somewhere. And you have to find it. I gave you also some nice pictures about this system. For large values of parameter phi, the movement of double pendulum is quite chaotic, very chaotic. And I will try to can we now try to make the picture, excuse me, možemo sad napraviti slikicu? I found some pictures in internet and would like to show you. Lasciamo pogledati. Bio je bookmark, ili tako? Aha. Ok. Aha. Ne taj, ne ovaj, to je drugi. Ne, ono prvo. Evo ovo, da. Ne, sada je prvo. Aha. Ne miče se ništa. Samo da vidimo. A treba ga potjerati, jel? Evo ga, da. It is absolutely irregular. This example is not quite realistic. Why? You wouldn't happen to find such thing if you make an experiment. Why? Because after some time it will come to rest. Why? Because in this model we didn't take into account the friction. Our model is without frictions, and of course it can be adapted. This Lagrange formalism can be adapted to include frictions as well. And maybe it's the point now to say that the whole importance of the equilibrium is that in fact in nature every movement will end up in the equilibrium because of the friction. but before it ends up, it becomes linear. So that's the picture. Just completely chaotic movement, and then the energy loss will bring you to a region where you are linear, and then you have exponential decay, as we have already seen with linearly damped systems. Thank you. Mm-hmm. Oh, there is no more. Thank you. Mm-hmm. Hvala lijepo. Ne drugo, ne. So, okay. Now I'm going to completely change the scene, and I will erase everything here and begin something which is theoretically new, but in the fact which you have in fact certainly noticed, that in such problems practically you have to solve two steps. One of them is to find equilibrium, and then the other to look at the small oscillations about it. The movement which go far than that are quite more complicated. For example, the movement of the satellite going from Earth to the Jupiter or something like that. That's quite a different bit of problem. That's first, and the second is that the main work is to find the equilibria, and the oscillations are routine. And that's so. Why? Well, because the finding equilibrium is a nonlinear problem, and the oscillations are linear. That's what it is. Okay. Světlo. The next exercise would be to do the same for the catenary. You see, double pendulum is in fact a simple catenary. It has only two items of the chain, and the only real difference is that the other end is free, but it's catenary, in fact, geometrically. So you will have to solve the movements of such a system according to the rule I described to you, not parameterizing, but linearizing the model from the beginning. But for this, you have to know where the equilibrium is. We proved that a catenary has a nice equilibrium. That we have proved. But I didn't tell you how to find it. And it's not easy. But it is easier if we have some symmetry. So let's look nogmaal at the catenary. We have V is equal to sum mi g of yi y to m. We have 1, 2, 3 particles. Here is 0. here is, I think, L, yes. And this is D1, D2, D3, D4. You may consider vibrations in the plane or in the space. These are two different problems, very closely connected. Because if you have a space catenary, which can move in all directions, and you take initial data only in the plane, then it will vibrate in the plane. So those plane vibrations are a sort of subset of the whole movements. Okay. So, and GI equals to xi minus x1 minus 1, 2, n plus 1, such that xy equals to y equals to 0, and xn plus 1 is equal to L, and yn plus 1 is equal to 0. These are the conditions. Those equalities are written down only to make this formula more symmetric. Otherwise, you would have to write a different formula from the left end and a different for the right hand. So, now, and I have proved you that if you look at this catenary in the space, so in L3, so to say, that means that the whole space is R to 3n. The geometry is in the R3n. Then it has a unique minimum point, and that the matrix of the second derivative, the Lagrangian, is positive definite, that we know. Now I make an additional assumption. I assume that my catenary is symmetric. What do I mean by that? That going from left and to right, you have the same bars. So d1 is equal to dn plus 1. d2 is equal to dn, and so on. And also m1 is equal to mn, and so on. m2, m n minus 1, and so on. Then I call my catenary symmetric. Okay. Well, this is a symmetry for this problem. Why? Because if you permute, the potential energy doesn't change. And what about this? It also doesn't change. You're just a numeration. So this now leads to the following map. xy, x1 goes to x0, xn plus 1, x1 to xn, and so on. And the same thing with y's. And you see that this map doesn't change your manifold, and it doesn't change your function. So what we do, we look for a solution which has the same symmetry. So we look a solution such that x1 is equal to xn, x0 is equal to xn plus 1, x1 is equal to xn, and so on. And the same with y's. It doesn't mean that we get this way our minimum. We get in this way the minimum among all symmetric positions. But once we found the minimum, we can check the sufficient conditions for the minimum in general. And if they're so fulfilled, then we have a global minimum. As I showed you, you can be cheated by jumping into symmetric solutions without asking. Think of that. The symmetric solution is here, but it's not a minimum. So you can, but it is a very good thing to first check this one and then to see. And so we do here, we find a symmetric configuration and then check the optimality in the whole space. So, we again, so I'll stop here and continue after the pause. This time's only quarter of an hour, okay?